Welcome to our midterm demo for SPUD, Single Core Processor Unit and Display, by Muhammad, Frank, Gabriel, and Valentina. Project SPUD is a custom CPU SoC built for RISC-V implemented onto an FPGA with an LED display for visual feedback. C programs can be directly ran onto the FPGA with the CPU. The system on a chip and CPU are implemented in Verilog. A custom display core drives our 64 by 64 matrix, and the arcade controller will be the main interface to control our interactable demos.
This is a 3D model of the design of SPUD. We designed and printed a platform with standoffs for the matrix, and this will also house the FPGA with our main PCB. We're currently working on designing some legs for the platform to sit on top of so that the matrix is angled towards the user rather than flat on a surface. And then we also printed an enclosure for the arcade controller to hold the bottom of the buttons and the wiring. Here we have our prototype for SPUD built for testing. We've got our Spartan S7 FPGA sitting on a platform that we 3D printed for the matrix. And then we have the matrix and the arcade controller connected to the main PCB. This here is a server we created to run our toolchain and allows all the members to SSH in for development of SPUD.
So we're going to be going over the SoC as a system at a high level, just so that we can understand what we're doing with the matrix and the arcade controller. So once again, the purpose of this project is to modify the existing SoC and add additional support for our peripherals that we have been adding, like this custom arcade controller and this matrix display. So we've created an instantiation of the display controller, which houses a display core. And this is one of the peripherals that is added into this AXI-bus tap controller that you see here, which basically just picks which peripheral we want to work with by mapping it out to a memory mapped register. So we've created memory mapped registers that map to these controllers, and once those instructions are sent into there, then we appropriately update the display or the controller. So for the matrix, which is the display, so we're using them interchangeably. This is the same thing as the display controller and the display core. We're just calling it matrix. We have our register is going to be at 96, and we have two offsets here because we have more than 32 bits of data getting sent through. We have the pixel RGB values and also the pixel index, so we know which pixel we're trying to access. So we've created two registers here for both of those informations, and depending on what address we are accessing, we'll know what kind of data we're getting, whether it's the address of the pixel or the data that's going to be updated into the pixel. And the matrix controller basically does all of that decoding, and then it interfaces with the matrix core, which houses the pixel memory that is used to get sent out into the display matrix. We're going to do a really quick overview of our Verilog for this matrix controller and then the matrix core. So once again, we've created this module, instantiated all of the appropriate or respective signals. And then you can see here we have the different register values that control what kind of data we will be receiving. We have an AXI handshake process over here. And then here is an instantiation of the matrix core where we will be sending in that data and expecting an output, which we will send back out over GPIO into the matrix. So I'm going to go into the matrix core now. And here we have the matrix core, we have pixel memory, and we are going through the different phases and updating row by row all of the pixels at a time.
Welcome to a demonstration of SPUD. I'd like to show you a quick overview of what we've been working on and jump right into our workflow and how we develop code for SPUD. So if you can see in the corner of your screen here, I have the matrix as well as the arcade controller, and you can see this cable goes right underneath and connects to our FPGA. There's a layer here. Keeps it nice and tucked in under there and clean. So the first thing we start with is our Vivado. So this helps us develop all of the Verilog and hardware description language for SPUD, and helps us generate bit streams for the FPGA. This is essentially our core and runs our hardware. We developed many of the modules that you see here in this hierarchical design. The first thing we start with is our synthesis. So we synthesize our design, and we get a good overview of like how much hardware we're going to need, what kind of hardware we're going to need. And we also like to generate this RTL schematic view where we can get really good insight into many of the modules that we develop for SPUD. You can see like this one is the SoC here. We can kind of see all the connections and dive into what exactly is going on. It helps us understand a bigger picture. Then we jump into the implementation. This will route all of our pins and connections and wires. And then finally, we have the hardware bit stream. So I already have a synthesized and implemented bit stream. I'm just going to open the hardware manager and load up a new version of our SPUD SoC. Perfect. So now our FPGA has loaded the appropriate bit stream such that it will run our SPUD code. So now that we have a CPU ready, let's jump into how do we write code for SPUD. So code for SPUD is very unique, and we have our own chain setup. So I'd like to start with SPUDENV, which is basically our environment for SPUD. This allows us to easily build, load, run, and simulate any piece of code that is built with SPUDKit. So this SoC right here on top is what we were just looking at in the Vivado, but these RV32i tools is what I want to get into on this portion. So we have under SPUDENV, we have awesome tools that we can use. Let's build our first program. So I'd like to show you Hello World, the very first program. So let's build Hello World. Using SPUD environment, we have a build script, and we can pass in the name of the project called Hello World. Pressing enter, we run our tool chains and cross-compile a version of RISC code that is developed for SPUD. So next, now that we've built our SPUD, let's figure out how do we run it. Under SPUDENV, we have a run tool where we can do run hello world. This will load the program onto the FPGA, and we can see under the UART console, it will print out hello world. Very cool. Let's show some other demos. One of my favorites is this donut program here, which we will build together. Once it's done, we can run it. We can see in the corner, we have our matrix running with a 3D spinning donut. What's really interesting about this program is that there are no floating points. You might be asking, how are you doing 3D rotation matrices and all of these decimals that you see in here without floating points? Well, that's because we use a fake float. We basically simulate it via software, since again, our FPGA has no floats, only integers. Moving on, I'd like to show another program. It's Arcade Display, and we'll show a quick demo of how we can test our controller here. So once that's loaded onto there, you can see we have these colored boxes that coordinate to specific buttons that we have on our arcade controller. This is our CPU, which is corresponding with our controller and can update the screen simultaneously. And this is all written through code. It's a very, very simple piece of code. And so that's all I have to show for now. In the future, we'll be developing more games that are interactive, like Snake or Tetris. And we're really excited to show everyone when it's done. But this is where we're at for now. We're still continuing to develop hardware and make it as best as we can. Thank you for watching our demonstration. Stick around for the final and we'll have more to show.
For our systems engineering specifications, we chose to highlight the following overall metrics: a processor's performance of 10 or more MIPS, an arcade button latency of less than or equal to 30 nanoseconds, an LED matrix refresh rate of less than or equal to 200 Hz, functionality including arithmetic, jump, and memory instructions, a board power consumption of 36 watts, an LED display power consumption of 20 watts, operational conditions with an ideal temperature range between 68 and 77 degrees, and a humidity level between 40 to 60%. And finally, a total price range between the range of 300 to 500 USD. For this demo, we chose the processor performance, arcade button latency, and LED matrix refresh rate to be our demoable metrics.
Our first engineering spec demo is processor performance, where we will be doing MIPS calculations. First, we started in simulation, where we executed 1 million instructions while an LED was turned on. As soon as those millions instructions were completed, we would toggle that LED. So here we are testing the output. We have a marker set at the beginning of that LED toggle and also at the end. So we take the time that it ends and it starts, do the calculations, and calculate the MIPS from there, which we can see over here. We have our simulation delay. It's the same for all 10 tests. And now we will go into the hardware delay. Here you can see the LED is changing very, very rapidly, so we connected an oscilloscope so that we can accurately measure how quickly this was. So here you can see the steady oscilloscope measures. Each box on the grid is 10 milliseconds, so you can see that it's 55 milliseconds for an LED to toggle, which is exactly what we calculated from the simulation. So once again, here we have that same test repeatedly 10 times. And then our MIPS calculation in here is the same as the simulation. And we have 18 MIPS, which meets our specification of greater than 10 MIPS excellently.
For the LED matrix display, we wanted to measure and verify the full screen refresh rate. Our display needs to update 32 addresses, with each address corresponding to 2 rows each, 64 rows total. So one full frame for our display is the time it takes to update all 32 addresses. We begin the measurement process by simulating the screen update process, and after finishing our simulation, as seen here, it yielded a full screen refresh rate of 6,650 microseconds, or 6.65 milliseconds. For the actual refresh rate, we measured that by implementing a flag signal that toggles on and off every time the 32 addresses are updated. And it measures the time it takes between each toggle. Each block in the oscilloscope represents 1 millisecond. And if we look closely at the displayed oscilloscope results, we can see that each toggle takes a total of approximately 6.6 milliseconds. Finally, if we compare the results, we can see that the simulated results match very closely with the actual results.
This test measures the latency of the input processing to the CPU, and we made this with some custom Verilog that we wrote. Each of the 10 buttons is its own test case, and when the button is pressed, the FPGA raises a flag signaling that the button has been received. On the oscilloscope, each square on the grid is 10 nanoseconds of latency, and we're measuring that latency by looking at the distance between when the blue input line starts to drop and the yellow FPGA line starts to rise. Here are the results of our button latency test. We had an average of about 12 nanoseconds per button press, which is a lot faster than we had anticipated. We can see that all of the buttons are under the 30 nanoseconds specification that we were hoping to achieve.